Okay, so welcome to the weekly colloquium at the School of Astrophysics. We are glad to have Professor Anirban from Saha Institute of Nuclear Physics today. So Anirban did his undergrad from the erstwhile Presidency College, as many of our colloquium speakers tend to do. And then he went to IIT Kanpur for masters, and then TIFR for PhD, where he worked with Professor Basudev Dasgupta, who some of you know, some of our students are working with him. He has even talked here before. So after finishing his PhD in 2019, Anirban went to Stanford in the SLAC National Accelerator Laboratory for his first postdoc. From there, he went to Seoul National University for his second postdoc, and then came back to India and joined SIMP as a faculty member. And Anirban works on the interface of astrophysics and particle physics, where he works on particle dark matter theories as well as neutrino, which he will talk about today. Anirban is also, within a very short period of time, he has become a very sort of a big friend of the department, because one of our students, Sridhakar, the second year student, is working with him for his MSc project. He has also been part of various committees in the department, and as one of the astro type people in the Kolkata, one of the few astro type people in the Kolkata area, he will continue to be part of various committees, etc. So thanks for doing all these things, and thanks for coming for the talk. So please.
Thank you very much, Rituvan, for the very kind introduction and for your nice words. And thanks again for inviting me here. Very happy to be here. I think this is probably my first talk of this scale here in Presidency since my time here as a student. So I'm very glad to be here. Is this a pointer?
Yeah, this is just a pointer. Slide will not change the last time.
Okay, thanks. All right. So, so when Rituvan asked me, initially I thought that I will talk about direct detection of dark matter, which is another side of my work, which are very close to my heart. But then I realized that this is astrophysics department, so probably also this is the year of, I think, 70 years of neutrino discovery. So I thought a talk on or colloquium on neutrinos will probably be more appropriate in this setting. All right, and more specifically, I'll talk about neutrinos, the role of neutrinos in cosmology. Okay, so I think most of you here are familiar with neutrinos, what they are. So this is a cartoon picture of all the particles in Standard Model. You see the quarks, and then there are these two broad families, quarks and leptons. And then also there are these gauge bosons or force mediators. But the curious thing about neutrinos in Standard Model is that all these other fermions, the quarks and the charged leptons, they have their so we can explain their masses using the Higgs mechanism. There's something called super spontaneous symmetry breaking in Standard Model that gives mass to all these particles except neutrinos. So but from oscillation experiments of neutrinos, we know that they have mass. They have to have mass, but we do not know how they get their mass. So that's what sets neutrinos aside from all other particles in the Standard Model. So in that way, they are very unique within the Standard Model framework itself. Okay, and they are also the only particles which interact weakly with, which only has a weak interaction, no other interaction, not the electromagnetic or strong interaction. Okay, so it's very difficult to detect neutrinos because you need very large detector. Also, the neutrino flux also has to be very high, and so it's very difficult to study neutrinos in a laboratory setting. Okay, so as I was saying, so this is a picture from the experiment called Project Poltergeist, which is the experiment where neutrinos were first discovered. So it was predicted by Wolfgang Pauli to understand the kinematics of beta decays, and in 1930s, and then it was discovered in 1956 in this experiment. You see this flag they have with the name of the experiment written. So here they detected reactor neutrinos, so neutrinos coming from the nuclear reactor, and so that was the first discovery. And we are almost like now we have completed 70 full years since that time. And so that's a very long time, and within this we have been able to measure various parameters of neutrinos. So we know that there are three flavors of neutrinos in standard model: the electron type, muon type, and tau type. Okay, and because they have masses and their flavor basis and mass basis, they are different. When they propagate, there is a mixing between different flavors. So if you start with a bunch of electron neutrinos and you wait for them to evolve for some time, and then you will, if you try to detect their flavor composition, then you will see that some of the electron neutrinos have converted into some other flavors, muon and tau type neutrinos. Okay, so there are this mixing. So all this flavor phenomenon is parameterized by some three mixing angles, and there are also these three mass states. So there are mass gaps. So these are the parameters in the neutrino sector that various experiments all over the world are trying to measure with more and more precision. And this is the precision that we have today. This is, I think, this is the yeah, this may not be the latest one, but should have updated this plot. But so right now we have very like a few percent level precision in the measurement of all these parameters. Okay. So that way we know quite a lot about neutrinos, but still there are many unknown questions. So the first one and the biggest one that I started with is of course the mass of neutrino. We do not, the standard model doesn't explain how neutrinos get mass, but we know that they have mass. So what is the source of that? And there are also other questions that you can ask, very relevant questions about neutrinos that you can ask, is that if you compare the mass scales of neutrinos with the other fermions, like the quarks or the electron, muon, and tau, there is a huge, many orders of magnitude mass difference or gap between these two scales, and which is kind of, to some people, that might feel very unnatural. So there has to be some kind of mechanism which sets the neutrino mass scale to be so light. So that's another question. And the fact that all properties of neutrinos cannot be explained completely within the framework of standard model, that makes the neutrinos the only known portal to the physics of beyond standard model. Okay, so there is something that we already know that is there beyond standard model, like dark matter, dark energy. So, and right now we do not know. We know that they exist, but we do not know what they are. So neutrino naturally could be a portal to that dark sector, because we know that standard model cannot explain the mass of neutrinos. So in that way, for a theoretician, neutrino act as a natural portal to the dark sector. So in that sense, neutrinos are very interesting. At least to me, they are very interesting. So you can ask many different questions also. What if they have any other interactions, not just weak interaction? And if there are more flavors of neutrinos and blah, blah, blah. Yes.
We know the mass hierarchy also, no? We don't know, right?
Yeah, that's a very good question. Right now we do not know which hierarchy is correct. So what Shomo is asking is that so we know that there are three mass states of neutrino, and we know that so we can now calculate two different types of mass gap. And we know that one of the mass gap is very small compared to the other one. So two of the mass states are sitting very close to each other compared to the other one. What we do not know is that the other thing, the third state, whether it's sitting above or below these two closely spaced mass states. So when it is sitting above, this is the normal ordering or normal hierarchy. When it's sitting below, it's called inverted ordering or inverted hierarchy. So yes, right now we do not know, but some of the observations, some of the latest data seem to suggest that probably inverted ordering is not the right one, but it's still not settled yet. Okay, so let's come to the main topic of this talk. So here is a timeline or the history of our universe very briefly, and I have marked out the epochs when neutrinos had some role to play. So if you follow this axis, this is the temperature of the universe coming down from the very high temperature of GeV all the way to present day temperature, which is of the order of milli electron volt. Standard model of cosmology tells us that active neutrinos, or these three flavors of neutrinos, they decoupled from the other particles in the standard model like electron, protons, neutron, and gluons. These neutrinos decoupled from the thermal bath at around temperature of 1 MeV. So that's the time of this formation of this cosmic neutrino background that I'll tell you more about. And since then, the neutrinos are mostly free streaming. They are not really interacting with other particles. And then there is another very interesting or very important epoch called recombination, when the CMB formed, the cosmic microwave background, the afterglow of the Big Bang in photon that was formed. And also neutrinos had some role to play during that time, because we know, actually we know from the CMB a lot about we learned a lot about our universe just by studying the CMB, the cosmic microwave background. And neutrinos affect the observation of the cosmic microwave background. And very late time, because we know that neutrinos, they have some mass, although very small. So at some point, they have to become non-relativistic. So when they decoupled here at around temperature MeV with a capital M, they have to be relativistic, right? Because their masses are of the order of maybe 10 to the power minus 2 or minus 3 eV. So at that temperature, they are highly relativistic. But at very low temperature, or in today's universe, some of them have to be non-relativistic. And if you have a bunch of non-relativistic particles streaming, free streaming in our universe, that affects the structure formation, the distribution of all the galaxies, galaxy clusters, etc. And that also, by studying this large scale structure, that also tells us a lot about the nature of neutrinos, or what is the total mass of neutrinos. So these are the three different areas where neutrinos are important in cosmology, but probably it's not exhaustive. But in this talk, I'll focus on these three things. All right, so first start from the beginning. So this slide I have stolen from Yvonne Wong. So here is a cartoon picture of what was happening around the temperature of MeV. So this is the time of Big Bang nucleosynthesis, when the temperature of the neutrino was, the temperature of the universe was low enough so that the first light elements were starting to form. And that's also the time when the weak interaction process was starting to freeze out. Freeze out in the, what do we mean by freeze out? So if you calculate the weak interaction cross section, let's say you have two kinds of particles interacting through electroweak interaction. The temperature dependence of that rate of interaction will be given by Gf square times T to the power 5. What is Gf? Gf is the Fermi coupling, that coupling that you have in the weak interaction. And T is the temperature of the bath, of course. And that rate you compare with the expansion rate of the universe. Because the universe is expanding, you can define an expansion rate which is just given by the Hubble parameter, and that goes as T square. Okay, so you see that this interaction rate is falling faster as temperature is decreasing. This interaction rate is falling faster, way faster than the expansion rate. So even if you start with a very large interaction rate, at some point this interaction rate is bound to freeze out. Okay, and for weak interaction, that happens around the temperature of MEV, and that's when neutrinos were decoupled from this bath of electrons. Okay, and then they started free streaming. So there is no more interaction. They're mostly non-interacting since after that time, and they started to free stream. Okay, and that's what forms this cosmic neutrino background. So you see this acronym many times. This is a cosmic neutrino background, just like cosmic microwave background. So we do expect an isotropic flux of neutrinos with a thermal distribution around us, which should have some temperature and some properties. And that should be, I think, my next slide. Yes, so this is the temperature of those neutrinos. So they are related by some order 1 fraction. If you are interested, I can explain to you later why this factor arises, which is very interesting. But yes, that's a very nice short problem to, yeah. Okay, so if you know the CMB temperature today is about 2.77 Kelvin, the neutrinos are slightly colder at 1.95 Kelvin. Okay, so this is the temperature of the neutrinos we expect that are there in the cosmic neutrino background. And this is the number density, which is also very easy to calculate, given that when they decouple, they were in thermal equilibrium, so they have a very well-defined number density. And since then, nothing is happening to their distribution, so their temperature is just redshifting as 1/A. Okay, and at very late time, when they became non-relativistic, you can write down the total energy density. This omega nu, that's a symbol for the total energy density in the neutrino sector. And you can write it down as a summation over the total mass of the different mass states of the neutrino. So this sum over m, this is basically the sum of all neutrino mass states. So these are the numbers that we know very well. Okay. What we do not know is that this m nu, the neutrino masses. We know what omega nu is, but we do not know what m nu is. Okay. So right now, there are multiple experiments which are trying to measure the sum of neutrino masses. So from one side, we have the neutrino oscillation experiments. They have some lower bound on the total neutrino mass. So if it is normal ordering, then the lower bound will be roughly around 0.06 eV. And if it is inverted ordering, it will be, I think, around 0.12 eV or so. Okay. And there are laboratory experiments which are trying to measure these sum of neutrino mass from studying the beta decay spectrum, the electron spectrum. And Catherine is one of those experiments, and recently they have put out a limit, this is an upper limit, of 0.45 electron volt. Okay, so neutrino double beta decay can also give the limit, but this is the most competitive right now. So this is just normal beta decay experiment. But so if you just go by this number, of course, this allows both normal ordering and inverted ordering. But I told you that nature seems to prefer the normal ordering, and that's because some other observables, like from the cosmology, which I'll come to later. And if you combine all the latest results, then we know that out of 3, 2 of the neutrino states have to be non-relativistic today. One of them, the lightest one, can be relativistic. I mean, that can be even massless. But the other 2, they have to be non-relativistic. Okay, so let's go to the different cosmological observables that help us to learn about neutrinos. So here, what you see is an n-body simulation of our n-body simulation of our universe. Okay, this is just a computer simulation. This is not an observation. But let me tell you what these are. So what you see, there are some regions which are very bright and some are very dark, blackish. So the bright regions, they basically mean that there are over density of matter. So you expect to see more galaxies or galaxy cluster or groups of galaxy clusters. And the black regions, they are mostly will be known as voids. There's nothing in the in those regions. Okay. And the distribution of these structures at different length scales is what we call the large scale structure. So this is just computer simulation, but of course we can do this experiment going to the by looking through a telescope and mapping the our universe, at least our local universe, and that also we have done. But let's first see what we expect if we have neutrinos in our universe with some substantial amount. Okay, so here I have taken two slides or two different n-body simulation results. The left one is with cold dark matter, just normal dark matter, so with very, very low temperature, not like neutrinos. The right one is with neutrinos as the dark matter. And the qualitative, yeah.
The hotter that you say, that's the dark matter candidate is neutrinos. All of dark matter is neutrinos, right?
In this case?
Yes.
Yes, in this case, all of the dark matter is neutrinos, but not maybe not of the mass eV, but maybe with keV mass also. So this is what we call the warm dark matter. Yeah. So the main difference between these two cases is that in cold dark matter case, we or in the simulation, we neglect the thermal velocity of the dark matter particles. Okay, it's very small, so that's why we just call them cold. But in case of warm dark matter, there is still some residual amount of thermal velocities among the dark matter particles. So, and that velocity has some role to play in the simulation, and that's what I'm going next. So as I was saying, after this, since the time of this Big Bang nucleosynthesis, neutrinos are mostly free streaming with these large thermal velocities compared to the cold dark matter. So when in our universe, the way structure formation happens is that, so we start with some very, very small amounts of quantum fluctuations throughout our universe, and these small fluctuations grow over time. And when there is a small overdensity of these cold dark matter, so by overdensity I mean something like a gravitational potential well, which has slight overdensity compared to the surroundings. And then what happens is that overdensity tends to accrete more matter from outside. Okay, that's how this overdensity grows, and with time that becomes a dark matter halo, and even after that it may form a galaxy and so on. Okay, and that's very easy to do because cold dark matter particles, which are leveled by this C, they are very cold and they do not have much large velocity. So when they fall into the potential well, they just remain there. But now, if there are neutrinos which come with these large free streaming thermal velocities, then what they can do is that they will try to erase the structure. Okay, or erase this potential overdensity, or sorry, the overdense region. Okay, and you can calculate this free streaming velocity of neutrinos, which is not surprising at all, directly proportional to the temperature of the neutrinos. And as the temperature evolves, this free streaming velocity also changes with time. But if you take the let's say the redshift of 100, okay, that's roughly the beginning, the initial time of all the n-body simulation, most of the n-body simulations, this free streaming velocity is quite large for EV, let's say EV mass neutrinos compared to dark matter. If you compare the dark matter velocity at that epoch, which would be very small. So neutrinos, they have very large free streaming, and for those overdensities which are smaller than the free streaming length scale, they will be erased. So these neutrinos, they will try to erase this or inhibit the growth of these type of overdensities, but the densities which are longer or bigger in size compared to the free streaming length scale, then these type of densities they cannot erase. So what is happening is that when the neutrinos are there in our universe, they are trying to erase the structure at small scales,
Scales
below the free streaming length scale, but they cannot do that for the large scales. Okay. And yeah,
This is happening only when they were at equilibrium with the other matter. Not in
no,
the
this is
later
happening. This is happening after they have decoupled.
But after they are not interacting. That's happening.
This is through just through gravity, as Shru Chaitanya was saying.
Very free stream.
I agree, but most of the effect comes from the initial condition. They change the initial condition of the initial power spectrum. They erase the power in the initial matter power spectrum.
No, this is happening, let's say, around after redshift of during the redshift of 100 or later. Yeah.
Much later recombination.
Yes. So this is a redshift 100 and later maybe.
Perfect. One is actually changing the initial perturbation
I
spectrum.
think that is the maximum.
No, this.
For example, warmed up matter, we have like proto-galaxy scale fluctuations getting erased.
So yeah.
Yes, but they have already that has been already erased at the time of the.
This is low.
No, yes.
See, this is the initial matter power spectrum.
No, this is the final. This is final power spectrum. This is what we observed.
Let's come back to it again.
Okay, so that helps me jump directly to this plot, which is the plot of the matter power spectrum, just for the junior audiences, junior members of the audiences. So what I mean by matter power spectrum is that, so I was talking about this this over densities, right? And that's kind of a field. You can write down this over density as a function of space and time. You take the Fourier transform of that. Then you do the ensemble average of the 2-point correlation function of these over densities in Fourier space. What you get is this matter power spectrum. Okay, so this just tells you. So you should think of this k vector in the momentum space. So k is the inverse of the length scale of a particular over density. Okay, so large k means small scale and small k means large scale. Okay. And this is the power spectrum that we see in our universe today. To be precise, this green one, and that's what we expect from the lambda CDM or the lambda, the standard model of cosmology. But now, if you add neutrinos, what is happening? That, as I was explaining, these neutrinos, they tend to erase structure, so the power spectrum is decreased at these small scales, at the scales below the neutrino free streaming length scale. And the amount of suppression is directly proportional to the amount of neutrinos. So omega nu over omega m, where omega m is the total matter density. So summing over baryons, dark matter, and neutrinos. Okay, so that's basically one of the observables, cosmological observables that help us learn about neutrinos. So. Okay, so the next one that I'm going to discuss is the cosmic microwave background. So I'm not sure if how many of this audience are already familiar. Maybe some of you are already quite familiar with this with the cosmic microwave background, but I thought just I'll go over the details again. So this is another very precise observable that has taught us a lot about our universe. We have learned a lot. I would say that we have learned the most from cosmic microwave background. So what you see here is what we mean by cosmic microwave background is the afterglow of photons since the time of Big Bang. As I explained, the neutrinos, they started free streaming after since the temperature of MeV. But in case of photons, because photons are the mediators of electromagnetic interaction, the photons were remained coupled for a much longer time. So that time, the formation of cosmic microwave background is around redshift 1000 or so. Okay, in terms of temperature, that's about 0.1 eV roughly. And you can actually measure that. So this is another isotropic background of isotropic distribution of photons. You will just go out, and it's now it falls in the microwave range. That's why we call it microwave background. And you can measure it, and it has the temperature, the brightness temperature of 2.7 Kelvin. And that's a constant temperature that's everywhere in all direction of the sky. Now, if you pull off this constant part, what we call the monopole signal, if you take out this constant part of the signal, then you are left with these small fluctuations. So these fluctuations that you see here are of the order of 10 to the minus 5. So delta t over t is 10 to the minus 5. What is the cause of these fluctuations, or the reason of these fluctuations? So the reason is the acoustic oscillations. So by acoustic, I mean the sound waves, very similar to what we see on the surface of the water. And we know that to sustain acoustic waves in any medium, you need two different types of forces. So one force which drives the oscillation, the other force which acts as a restoring force, which tries to pull it back. So in this case, these acoustic oscillations were happening in the bath of photon and baryons. And by baryons, I mean all charged particles, so electron and protons and everything in the early universe. They are tightly coupled through the scattering of Thomson scattering, which I'm sure you have heard of. So they have this thermal pressure, which is always trying to push a slight over density in the bath, and the gravity is of course always there, and gravity is trying to pull them back together at the bottom of the potential. So that is described by this well. So this schematic is taken from the very famous popular website or notes made by Wayne Hu. So there is this oscillation. So the forces are shown by the springs, and there is this oscillation going on, and that's what form these fluctuations that you see in the CMB sky. Okay, so how do we learn about our universe from the CMB sky? So what we do is again measure 2-point correlation function. So this thing comes up many times in cosmology, observational cosmology. So if you now go to the CMB sky, you measure the temperature in two different directions, which are separated by some angle theta. Okay, and you correlate the delta t's in these two different directions, and then you take the ensemble average over all directions in the sky, and then you take the Fourier transform of that function c theta, and that's what gives you this plot. Probably all of you have seen this in this quantity or this plot in some form. So this is the Fourier transform of this quantity or this 2-point correlation function in the CMB sky. The x-axis here is an angular scale. So 90 degree, that is a large angular scale, and toward right is a small angular scale, and the top x-axis is the multiple moment. So if you take the Fourier transform of a function which is a function of angle, then you go to the space of spherical harmonics. So you get these multiple moments L. This is that L. Okay. So large angle means low L. So you start from L equal to 2. And you go toward very high L. So this is small angular scales. And these red dots or these red circles are the data. And the green line is the best fitted lambda CDM, or the standard model of cosmology. So you see how well our 6-parameter model of cosmology can explain the CMB data. And this thing has been done in the temperature map. So this delta T, delta this is a temperature correlation, but you can also do the same exercise in the polarization. So photons also have these two polarizations, right? And you can do temperature polarization, and you can get all these observables. And this particular data is taken from the Planck experiment. So Planck has been one of the most successful CMB experiment that we have had by the European Space Agency. Okay, so in cosmic microwave background, the neutrinos, the effect of neutrinos in CMB comes in two different ways. So one is the matter density. So as I said, neutrinos are massive. We do not know what their mass is, but we know that they have to have some mass. So they add to the matter density. And this equation probably some of you will remember. So this is nothing but the Friedmann equation. This explains the expansion rate of our universe. And on the right hand side of this equation sits this rho total, or the total energy density. And in the matter domination era, if you add neutrinos, so that adds to the total matter density, and that changes the expansion rate of the universe. And when you change the expansion rate of the universe, you change the amplitude of this power spectrum, say the CMB anisotropy power spectrum. And by measuring this amplitude, we can tell how much matter there is in our universe. The second thing that neutrinos affect is through, again, this large scale structure. So there's this thing called CMB lensing, which is described in this schematic. So as I said, the CMB photons, they started to free streaming after the time of recombination, so around redshift 1000. And we are observing them here, right, in today's universe. And there is a long path that these photons had to take, say, between these two epochs. And they had to go through this large scale structure. Okay, and as the structures or galaxies and clusters of galaxies were forming, these photons will be bent by the gravitational pull, right? And this distortion, that is an additional distortion than what we already had in the CMB sky at that time. Okay, and this is what is called the CMB lensing. And by studying this extra amount of anisotropy that is introduced by large scale structure, we can measure the amount of neutrinos. So together, these two are the main two things that massive neutrinos have on CMB. Just to complete the story, so this is the latest result from the Planck collaboration that we have. So on the left hand side is the posterior for the total number of neutrinos. I'm not going to into the detail of the definition of this parameter ineffective, but that should be around the number 3 because of the 3 flavors of neutrino, 3 masses, 3 states of neutrinos. And we say it matches very well to that number. And on the right hand side, this is a posterior for the total mass of neutrinos. Okay, so far, if you look at this black line, which uses the temperature and the polarization data, it also gives us the tightest constraint. And if you compare, so this is sum of neutrino mass in EV, and if you compare with the 0.06. Yeah, 0.45. No, I was actually wondering about the normal ordering number, but that's probably not this data. If you add more data. Yeah, this is the total mass. Yeah. Yeah, no. I was thinking that there are some combinations of data with CMB that gives you even tighter constant, but probably this plot doesn't have those numbers. Yeah. Okay, but anyway, so these are the some of the numbers that we have. Again, these are upper limits that we have from the CMB. And now you can see that CMB or the cosmology tells us more about neutrino than just beta decay experiments or Catherine experiments. But of course, you have to assume the model of lambda CDM. Okay, so the last topic. So how much time do I have? Okay. Okay. Right. So the next topic that I wanted to mention is something that I have been working on for last few years now, which is on the beyond standard model interactions of neutrinos. So far, whatever I have discussed is just comes from the standard model of neutrinos, just their masses and their free streaming properties. But here I have highlighted this one particular question, is that because we know that they are the sure shot portal to the dark sector or beyond standard model physics, it's very natural to ask whether they also have some additional interactions, just not just the weak interaction, but something else. Now, to go ahead, we have to have some kind of model in our mind, and we'll take inspiration from the electroweak interaction again. So on the left hand side here, I have drawn this 4 Fermi operator. So in the language of QFTs, this type of Feynman diagram represents neutrino-neutrino self scattering. Okay, and the interaction rate of this process is proportional to GF squared times T to the power 5. So GF, I have already explained, GF is the Fermi coupling and T is the temperature. It's actually very easy to understand how you get this particular power of 5. So 3 just comes from from the number density, and the other 2 powers comes from the cross section. So similarly, with a very model independent way, what we are going to assume is that there is this new effective operator in the Lagrangian that we add beyond standard model between 4 neutrinos, and we introduce a new coupling G effective, which can be written as some other coupling. So G effective, of course, if you calculate the mass dimension, G effective has to have some mass dimension. It's not a dimensionless coupling. So, but we in our mind we think of this G effective as some G phi to the power 4 over M phi 4, where M phi is the mass of this new mediator. Okay, just like the W or Z boson. So phi would be our new mediator. Could be scalar or vector. And if you again calculate the interaction rate when the temperature is much smaller than the mass of the mediator, then again this interaction rate will go as T to the power 5. But now with this new coupling, G effective square.
Addition to neutrino self-interaction.
This is still 2 neutrino self-interaction, but now we have an additional channel for scattering. Yes. Yeah. So in standard model, neutrinos only have weak interaction, nothing else. Yeah. 4 neutrino means, so you should read this as like time is going this way. So you have 2 incoming neutrinos, 2 outgoing neutrinos. Same neutrino. Yeah. In the Lagrangian, you have to have 4 neutrinos, but yeah.
Harmonic coupling, you write the fourth term.
Yeah.
That's why GF has M to the minus 4.
Yeah.
The dimension is 6.
Yeah, this is a dimension 6 operator. Just like the 4 Fermi effective theory that we have in standard model, or the low energy effective theory of standard model. Okay, but the main difference between this coupling or this interaction and this one is that we are going to assume much larger coupling strength or much larger or stronger interaction rate, and you will see that actually those numbers are allowed. So it's not like we are talking about nonsense, but right now we do not have precise enough data to constrain an interaction all the way to the level of Fermi coupling. So this is a plot which should give you some idea about what type of coupling strengths that we are talking about here. What I'm plotting on the y-axis is gamma over h. Gamma is the same interaction rate and h is the Hubble expansion rate. So this is a very useful quantity that cosmologists often plot. So that tells us if this quantity is above 1, that means that interaction is very efficient. So the interaction is happening in our universe. But when it goes below 1, that means the interaction has kind of frozen out. The rate is smaller compared to the expansion rate. This orange line is the line for the weak interaction, just in standard model. So you see that this interaction, so the y-axis, the x-axis is the redshift. So this is early time, this is late time. And you see that this line, the Fermi, the electroweak interaction, they decouple much earlier, as I explained during the time of BBN. But the type of
line was showing.
Yes, with GF, yes, Fermi coupling, 10⁻⁵.
Semi. So
Yeah.
during Big Bang nucleation.
Yes, exactly. So yeah, so I have also marked out this epoch when that happened. They are not exactly at the same time, but that's because I have ignored all the details of the neutrino decoupling. If you take care of all these things, you will find that this happens right around this time. But I have also plotted these other two lines, this solid line and this dotted line, which are the typical values of coupling that I will assume in our work. Okay. And you will see that for particular this one, this interaction decouples much later, just around the time of matter radiation equality. So that's roughly slightly before the time of recombination, so the formation of CMB. And that's very important because whenever something new happens, some new physics happens within the 1 decade before the time of recombination, CMB probably will be your best shot to constrain or to study that.
You have stronger coupling strengths. So wouldn't that also push because the matter radiation equality that you were showing around redshift of 10,000,
Yeah.
that's the standard, standard cost.
Yes.
But if you have stronger coupling of neutrino, would it not push? Because I think when you have the neutrinos coupled more strongly, as you said, that the decoupling happens much later.
Yes.
From photons. The neutrinos decouple from the photons later.
No. Yeah. So that is, I think I did not explain that. So when I am introducing this new interaction, so this is only within the neutrino sector. So there is no additional interaction. No. Yes. So everything is happening within the neutrino sector or within the active neutrino. Self-interaction. Yes. So so even in this picture, the neutrinos decoupled from the standard model at around time of, again, BBN, but they were still coupled with each other. Okay, so that is very important. Yeah, so in the standard scenario, after this decoupling, these neutrinos were free streaming. Okay, now in this case, they are not free streaming, so they will remain coupled all the way until here. They will start free streaming after this. Okay, and that has a much big role in the CMB or in large scale structure. Yes.
Then interaction change the neutrino power spectrum.
What do you mean by neutrino power spectrum? Like in
that is within the neutrino.
Yes.
But how if it is not interacting with the standard model particle, how it's going to transfer that change to the this sector?
Yes, so that's what I'm going to explain. But you also mentioned this that will change the neutrino power spectrum. But yeah, maybe I'll talk about that at the end of my talk. But let me first explain. So whatever is happening within the neutrino spectrum. But what Shomya is asking, how that transfers to the ordinary sector or the visible sector. So if we talk about CMB again, there are two main effects that happens in the presence of neutrino self interaction. Okay. One thing is the enhancement of structure. So as we were discussing, in the standard scenario, the neutrinos were free streaming, but with this new additional interaction, they are not free streaming. They are doing this zigzag motion, right? And what that does is that supports the growth of structure, because now that large free streaming velocity of neutrinos that's gone, right? Now these structures or these fluctuations can grow much more easily. So that leads to some enhancement of this power spectrum. So this is again the CMB anisotropy power spectrum. Yes.
Below the
Exactly.
damping scale or
Yes.
scale of standard.
Exactly. Yeah, so that's precisely what is happening. If you see, so here the standard model line is a black line, which is pretty hard to see here. I agree, but the neutrino interacting case is the red one, and you will see that the red line is sitting above the black line in all these peaks, but not here. So this is still at large scale, but with at the small scales, this red line is above the black line, so which tells us that there is a slight enhancement in the power spectrum or structure. The other thing that happens is a bit more subtle, which is a slight phase shift to the right hand side or towards small scales in the CMB power spectrum. So there is a very nice paper, all analytical paper, there is no numerics, paper by Sergei Bashinsky and Uros Seliak, where they have calculated this amount of enhancement and the amount of phase shift as a function of neutrino species, and so this gives rise to again a phase shift. I mean, if you want, I can give you some explanation of the reason behind this phase shift, but it's not very easy to understand in layman's language. And so this is what you get. So now you have this new model of neutrinos, and you run your model with the latest CMB data. So in our case, we use the 2018 likelihood of Planck, which was the latest one at that time. So this work was done around 2020. And this is the posterior that you get for this new coupling. So what I'm plotting here is the log 10 of this G effective. Okay, so you should use for so -3 means 10 to the power -3 MeV to the power -2. And so the left hand side of this plot is the lambda CDM limit or the standard model limit, right? When the coupling is very, very small. So the CMB data doesn't have any sensitivity at all, so it just flattens out here. So that is the standard limit. But curiously, there is also this, this is a bimodal posterior. There is also this additional mode at larger coupling or stronger coupling around -1.9 or -2. Okay. And you can do this in different ways. So you can say that let's say all three neutrinos are coupled, or you can say the only two are coupled, or only one is coupled. So these are denoted by these three different line styles. So 3 coupled, 2 coupled, and 1 coupled. And we showed that there is a strong preference for the 1 coupled scenario. So what that says is that one flavor of neutrinos has this additional interaction, but the other two, they do not. But if you include all 3 flavors, then there is a very like a huge suppression of this second mode. So that's probably not preferred by the data. And the right hand side plot is the joint posterior with the Hubble constant at present time. So, and the reason behind this showing this is that this neutrino self-interaction idea is very old. Is since the time, I think, from 80s or 90s. But in recent years, people started working on this idea again, and that's related to this tension called Hubble tension, which I'm sure some of you or maybe all of you have heard is the discrepancy between the two measurements of the parameter H0, the Hubble parameter, one from the early universe like CMB and one from the late universe like supernova data. And this, as you can see, that this large self-interaction tends to give you a larger value of H0. So which is why people again got interested in this model of neutrino self-interaction, and they started working. But what you can see here is that if you allow only one neutrino to interact, so this is this green posterior, green contour, then the amount of shift to the higher H0 is not sufficient to explain the tension, okay, or solve the tension. Yeah. Yeah.
Maybe you can explain later. So I'm not sure what when you are doing that flavor specific coupling. What do you mean by that?
Yeah, by flavor specific, I mean so this thing. So only one flavor has interaction, or two flavors.
But distributed by one third kind of thing, or
No, the total mass will be so the for example, the CMB CMB data is not sensitive to the mass ordering right now, at least. Okay. Yeah. Yes. So it doesn't matter how you distribute the mass. Okay. Yeah. So but that it is sensitive to, because whether all three neutrinos are free streaming or only one is free streaming, these two have different effects.
That
You are saying
depends
how
on
is that being implemented?
ratio.
Oh, the interaction. So okay. If
ratio how you are choosing or
okay, so if I understand your question correctly, what you're asking, let's talk about the 2C thing. So here I have two interacting neutrinos and one non-interacting. So the non-interacting is nothing is happening. So in the two interacting case, you are asking what is the coupling strength for these two states?
the fraction.
Fraction of masses.
Masses.
Oh,
One
that
third.
yes. It actually, yeah.
Number what?
It's just one third. Actually, it doesn't matter whether you do it 0, half, or whatever, one third. It doesn't really matter.
But
I'm talking about the mass.
Mass doesn't matter.
Yes.
Mass doesn't matter.
Yeah.
But the interaction matters.
Interaction matters.
matter.
Yes.
How you are distributing in this.
Yeah. So in all cases, in all cases, I have three flavors of neutrino. But so in different things, I have only one neutrino interacting, 2 or 3. So that is the amount of interacting neutrino. Yes.
Compared to mu or mu. So I think the number density distribution is always kind of one third. But I think that's what he's trying to say. Yeah,
and also in case of cosmology, so neutrinos, because we are talking about a very long time scales, so it's much better to so you will always get the equipartition.
My point, Anirban, was that in the right hand side plot, your one species coupling, one species enhanced coupling, the 1C case, that is when you have interaction in one neutrino, that doesn't, it doesn't increase your Hubble parameter that much.
Yes.
Whereas that is what is favored in the left hand side more.
Yes. Yes. And that's actually, we also know why that is happening. That's mostly happening from the polarization data. So the polarization data is same Planck polarization data, at least, is much more sensitive to any new physics in any shift of these peaks and amplitude suppression or enhancement. So once you, if you, for example, in this red line, if you do not include the polarization data, just use TT, temperature, you will see that you again get a very large enhancement, even in the 3C case, even for the red line. But once you include the polarization, that's gone. So that actually that point was one of the main results of our paper. We showed that if you use the latest Planck data, that enhancement for the strong interaction in the flavor universal case is gone. That's not there. Yeah, I mean, I myself is not a very big advocate of this solving this Hubble tension, because I myself have some doubts and other things, wow, how genuine this tension is, but that's another topic. Okay, so the last thing that I want to mention is, and I'll stop with that, is a new project that I'm doing with my collaborator, my postdoc here, Ranjini Mondol, and my collaborator at IISc, Ranjan Laha, is we are trying to use the data from UVLF data, or UV luminosity function data from JWST. And what can this new data tell us about neutrino self-interaction? So I have shown you the effects of this additional neutrino interaction has on CMB observable or CMB anisotropy power spectrum. But parallelly, there's also something happening in the matter power spectrum. So you'll remember in one of my earlier slides, I flashed the matter power spectrum. So here what I have done is that I have taken the lambda CDM power spectrum, and I have divided the power spectrum that you get with self-interacting neutrino. I've divided that with the lambda CDM case. So at large scale, you see that these two power spectrum are equal. There's nothing happening. Then there is a bump at a particular K scale, and then there is a suppression at small scale. This suppression is kind of we expect, because these are massive neutrinos compared to lambda CDM. So as I said, they tend to erase structure at small scale. But then there is this additional bump in the power spectrum. Okay. And you can actually, so this plot was done with this coupling strength, log G effective 10 to the minus 2. And you can actually get this scale just by calculating the time or the epoch when these neutrinos got decoupled from each other. So with this particular coupling, you can calculate that time, and that scale comes out to be of this. And that's a scale exactly where you also see a bump in the matter power spectrum. Sorry?
Some benchmark coupling.
Yeah. So if you decrease the coupling strength, then this peak just shift to the small and smaller scales.
For that peak, so that means that we are having enhancement of power compared to lambda CDM.
Yes.
You're saying that scale is related to the epoch when the neutrinos decouple.
Yes.
But I thought that neutrinos are okay.
Oh, you mean that,
so you are saying that this is related to the time scale when neutrinos decouple, and they would decouple much later if they have this additional self-interaction.
Yes. Yeah.
You have more. In fact, it inspires structure formation.
Yes.
Compared to CDM, because it's decoupling later. That's why you.
Yes.
Right?
Yeah.
That's why you allow more formation of structure. You are not
right.
raising.
Yeah, that's a rough way to understand.
This means that it's such a pinpointed scale. So that's what.
Exactly. I mean, yeah, I mean, you would expect that if there is enhancement, there should be the enhancement should be everywhere. Yeah. Yeah. So yeah, I mean, again, you can go back to the basics, like you can look at the equations of linear perturbation theory and try to understand why this is happening. It's happening because I can give you some details. So it comes from the anisotropic stress in the Boltzmann hierarchy, because when you have free streaming neutrinos, not just neutrinos, any free streaming species, you have large anisotropic stress. But when you are stopping neutrinos from free streaming, you do not have that anisotropic stress, and that plays a huge role in the growth of these metric potentials. because there are two different metric potentials, phi and psi, and the difference is exactly given by the anisotropic stress. And that's what gives rise to this growth of structure at that particular scale when the neutrinos are starting to decouple or starting to free stream. Okay, so now we can take that matter path spectrum, and in your model you can calculate the UV luminosity function. Okay, what is UV luminosity function? It is just the number density of galaxies within a particular magnitude bin. So I'm guessing that all of you understand what magnitude is. Basically a measure for the luminosity of the galaxy, and you can plot the number density of galaxies in the magnitude bin. The yellow line here is the lambda CDM, and the green dotted line is the neutrino interaction case. So you see that there is a small enhancement, and we have done this at two different redshifts. We actually are taking data from other redshifts also, but these are two example cases. In both these cases, we have small enhancement, and these are some of the data sets that are coming from. It's a like a very ongoing thing, and we have data from the JWST. And of course, they still have very large error bars compared to the change that we expect in theoretical model. But still, just with this data, if we compare the result, this is the same posterior that I showed earlier with the neutrino interaction strength. The blue line is just using the Planck data, and the red line is Planck plus this UV luminosity data from JWST. And you see that there is a slight enhancement or slight improvement in the limit that you can put on the neutrino self interaction. So here I'm not talking about this additional peak for larger coupling. I'm talking about this lambda CDM limiter. So we are just trying to see how deep into this GF regime we can push the limit, or what we can tell about the neutrino interaction. Other than the electric coupling. So we see that there is a small enhancement, and we hope that as we get more and more precise data from JWST within, let's say, next 1 or 2 years, we can improve this even more. So this is still a very ongoing work, and we hope to get it out soon. Okay, so I also had a couple of slides for the Ptolemy experiment. If you want, I can explain it. But this is an experiment which are trying to detect this cosmic neutrino background in laboratory. But I think for the interest of time, I'll just stop here. And this is the summary. And I'm not going to read it, but I'll just stop. And thank you for your attention. Thanks.
Okay, questions, comments?
It's a very difficult job. Yes. Yeah, so in this collaboration, what they are trying to do is they are looking for this neutrino capture process. Okay, not this one. So this is the beta decay process, right? And this is the neutrino capture process. They are using the tritium nucleus, so the 3 isotope of hydrogen. And these neutrinos from the cosmic neutrino background, they will come and they will be captured, and you get out an electron. And this electron will be very low energy. The main challenge is to actually that's not the main challenge, but what they're trying to do is to get it energized by putting some electric fields and stuff to high energy so they can detect it. But the thing is that, so one thing is that the flux of these cosmic neutrinos is very low, and the cross section is also very small. So you need there is very large amount of tritium. Or what they are trying to do is that they are trying to absorb this tritium on a monolayer graphene. So they have a sheet of graphene with these carbon atoms, and this tritium will come and sit on top of these carbon atoms. And that will probably help them to scale up their experiment. So they need a lot of tritium to get some numbers, so get some things. I think I saw at some slide or some talk that if you have 100 gram of tritium, you expect to see 7 events in a year. And 100 gram is very, if you know graphene is a very light material, right? Getting 100 gram of graphene is like almost unimaginable at this point.
Because there are other neutrinos
That's
also
what
Yeah.
my question was. This specifically that energy scale, it interacts there with the energy of the background neutrinos, or they interact with all other neutrinos and they have to subtract the that part to actually get the background.
Yeah, I mean, I do not know what would be the final energy of the neutrino. So they will accelerate this. So this would be the energy spectrum of the neutrinos, okay, at very low milli-electron volt. But what they are trying to do is they will put some electric field to energize it. But I'm not sure what would be the background flux or what is their background static. Yeah, these are very low energy neutrinos.
Experiment targeted only for the low energies, or they have to filter out separately?
Why they always say that?
I explained it all.
Yeah, I mean, yeah, I mean, this idea has been, this collaboration, I mean, they have been working on this for some time now. I think they also have a prototype. I think they built a prototype at Princeton, but now there is a collaboration. I think they have moved to LNGS in Italy. But I'm not sure what is the exact current status.
They just want to give a clever answer which will seem right but ultimately be wrong. That's why they named it Ptolemy.
Yeah. Yeah.
Other questions?
Yeah, I had a question.
No, but first one is a comment.
Oh, actually, I also want to comment on the neutrino power spectrum that you made.
Yeah.
Okay, but please go ahead.
So you did the same thing with when WMAP result was published.
Okay.
Then we used the UV luminosity function at low redshift, around redshift 6 or so, to constrain the total mass of the neutrino
Okay. I
along
see.
with WMAP thing. And at that time, WMAP was giving something like 2 electron volt.
Okay.
And if you combine with this UV luminosity function,
When was this?
13 or
So then, why didn't you use HST data at that time? Because I mean, I think HST has more data at low. Sorry.
UV luminosity function data is the HST data.
Okay, but
And combining with the
combining with WMAP. Oh, okay. Yeah.
like the
Yeah.
way you are AWST,
Yes.
that will give the WMAP data with the HST UV luminosity function
Right.
data, which tighten the constraint like even 1 EV or something like that. At that time.
Okay. I see. That is interesting. Okay.
Similar to
You were looking into this the suppression of the
Suppression of the
UVLF. Okay.
suppression these things.
Okay.
So
Yeah.
that's similar
I
to
see. That is okay. That is interesting. I mean, people are also right now combining. I think I actually know there is another group who are also working with the HST UV luminosity function for this same neutrino self-interaction model. But yes, neutrino mass also can be constrained in this.
After that,
Yeah.
I have not looked into that. Anyway, the question was okay. You can now give me that power spectrum thing.
Oh yeah. So so the thing is, you mentioned about neutrino power spectrum, right? So in principle, you can, so the way we measure the CMB sky map, so the same thing actually also can be, so this is a far-fetched thing. So this thing can be done for the neutrino sky also, the CNEOB. So of course, it cannot be done maybe in the next 10, 20 years. But in principle, you can actually measure the anisotropy in the neutrino sky. Okay, that will also have the signature of everything, all these things, neutrino mass, neutrino interaction and everything. That would be the best observable ideally, but of course we do not have it now. Yeah.
So, can you go to the plot where we are doing the self-interaction?
This one.
Yeah.
Hmm.
No, with the one where it has alternative species of 4 point something.
Oh, okay. This. Hmm.
It's black line, which is the ineffective of 3.046, and
Hmm.
you have the red one, which is adding the self interaction.
Yes.
Then there is the green one.
Yes.
What is that? You have
So-
four species.
Yes, that is adding another species of neutrinos.
Is that massive or just like this?
No, I think in all these cases, the mass is kept the same. So there is no variation in mass.
Sterile or
Yeah, I mean, it's up to you what you want to call that extra state. But cosmologically speaking, it's just additional state of radiation, so that the total ineffective comes out to be roughly 4.
crazy mass.
No, it cannot be. Yes, yes, yes.
What you see there is that
So
you have
yeah, so that's again, it's very hard to see if I have the bigger plot. Okay, no. So the thing is, why I was plotting with this ineffective is that. So I told you about this red line, right? So what this interaction does is it enhances the path spectrum and pushes it to the right. But if you increase n effective, that does exactly the opposite thing. So it suppresses the power spectrum because of silk damping, and it also shifts it to the left. So so that is again comes in the context of explaining this Hubble tension with this neutrino self interaction. Just neutrino self interaction doesn't give you a good solution, quote unquote solution. But if you also allow n effective to go up, then you can maybe get a better fit of the data.
is with adding the self interaction or without adding?
No, this is just without. Yes, yeah.
In
Yeah.
one case, to add additional interaction. In other case, you just increase
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 the
of
energy density. Yes, yes.
For the red guns, red line,
Hmm.
being through. So you are saying that there is a shift toward the lower L value, higher multiple value.
Yeah.
That means smaller angular scale.
Yes.
Why would that happen? So you have the peaks being shifted to. Does it shift the first peak?
No, so both these effects, they are more applicable to the high tail, high L tail.
That's nice. So
Yeah,
You see
yeah.
the more shift in the higher.
For this, there is not much here. Yeah. Hmm. Yeah.
But why would it shift to smaller scale? I mean, why would the peaks? That's what is happening.
Yes. So the peaks are moving to the small scales. Yes. Yeah. So I mean, so
smaller peak scale, to be more specific.
yeah, they're the same. So one way to people try to understand this is that what is happening in lambda CDM when neutrinos do not have the interaction, they are free streaming, and because they are relativistic, they are moving at the speed of light, which is way higher than the speed of sound in the photon baryon plasma. And what they do is that, because this is still at the end of radiation epoch, so neutrino, they have a very large energy density, and when they are moving at a supersonic speed, they try to drag the perturbations ahead of the sound waves. So that is one way to understand how these peaks shift to the small scales.
Then when you increase the ineffective, you have an additional species. First
Hmm.
of all, power is suppressed. Why would that happen? Why would power be suppressed if you have an additional species?
That just comes from the I think that just comes from the silk damping. So because you have more radiation, so that changes the time of matter radiation equality, and you get
So you're saying that you have a damping thing, because if you increase the number of neutrino species, then yes, you have more radiation.
Yeah.
Correct.
And
you're talking about
the silk damping length scale, that yeah.
Species, but these neutrinos are still decoupled from the photons, right?
The neutrinos are decoupled, but the matter radiation epoch is now shifted to a slightly later time, because
Quality you are talking
yeah, matter radiation equality.
reaction.
that changes the silk damping time scale or length scale.
Push further
Yes,
because of an
yes, yes,
structural formation because matter is still coupled to radiation.
yes, yes.
This is the not structure formation here.
Yeah, I mean,
No.
The contributions of the photon.
So that's what I'm saying.
But
This
the
is not.
neutrinos.
This is all changing in the initial. That will later affect the structure formation.
No, I think here, no, here matter is, sorry. When you see the CMB power spectrum, we are looking at the fluctuations in temperature and the photons are still marginally coupled with matter. After recombination, they will be completely decoupled. So they are still, when you see the CMB power spectrum, matter and radiation are still coupled. But the neutrinos are supposedly decoupled, but they have decoupled much before. They have decoupled from photon. What Anirban is trying to say is that now you have more radiation, then the energy density of radiation and
so that equality happens at a later time.
But that's why you forget about whether you add interaction or not. That's how constrain the number of PCs from the CMB spectrum.
correct.
That's why we put 3.0 or whatever number or even was.
So what you are trying to say is
That changes
this
the
green change is majority due to the initial perturbations.
initial part.
But what do you mean by initial perturbation? The primordial power spectrum.
It changes the primordial power and later on something.
Primordial power of what? Of matter or of radiation or of what?
This is changing the
When we talk about primordial power spectrum, we talk
What?
about matter.
Matter.
Matter power spectrum.
matter power.
Matter power spectrum.
Matter power spectrum and in this case CMB power spectrum.
So I can tell you one thing. So when we solve this, when we calculate this CMB power spectrum, what we solve is this hierarchy of Boltzmann equations. And we start with the primordial power spectrum, and that primordial power spectrum has been taken to be the same in all cases. So that's a scaleless Heisenberg power spectrum. So K over K naught. Yeah, that is the same. We did not do anything to that power spectrum here. So whatever is happening is just from the evolution. Yeah.
Any other question?
I have one.
Yes,
Yeah.
please.
So my question is that compare this normal picture and inverted picture, this the happy problem.
Yeah.
How the S4 surveys are coming up, like 10 years for complete
Mhm.
direction one also. Is it for when there is this prospect that it is cosmologically we can resolve this problem, or will it shed light on it? Because all these things have a separate approach to measure this parameter, and
Mhm.
quite
Okay. Point.
it has bias, but less in bias. Of course, there is not bias. Do you think that these experiments would probably be plausible to give more answers to that problem? The normal and
Yes. Yeah. That's a very good question, and the result is yes, of course. More data we have from cosmology that will try to help us to constrain the more the total neutrino mass.
But
Yeah.
not the hierarchy.
I don't
No,
know
but
what is it?
no, if you go to the level of, let's say, 0.06 eV, then you are already saying that. Okay, so let me, if I think I do not have the. So what I'm trying to say is that in inverted hierarchy, that sum of neutrino mass is predicted to be around 0.12 eV. Okay, I do not remember the exact second digit, but it's around 0.12 eV. In case of normal ordering, that is 0.06 eV. And now even with the current data, some of the cosmological data is already in tension with the inverted ordering number. So there is a slight hint, I would say, that inverted probably normal ordering is the right one, but we are not sure yet.